In this video, we'll take a look at section 12.1, a goodness of fit test. This test is for qualitative data instead of quantitative data, and think of it as one row in a two-way table. So we first of all need a different distribution since we're going to be taking a look at qualitative data. And the distribution we're going to look at is called a chi-squared distribution. And characteristics are the chi-squared distribution is not symmetric. The shape depends on the degrees of freedom, just like students T. As the number of degrees of freedom increases, the chi-squared distribution becomes more nearly symmetric. And the values of chi-squared are not negative. So if you look on the right, it's got some examples of what a chi-squared distribution looks like with different degrees of freedom. And remember, for students T, degrees of freedom was sample size -1. It'll be something similar for chi-squared. The area underneath the distribution, though, the probability distribution, is still 1. So how do you find critical values? So remember that critical values are the chi-squared values that go with certain areas in the tail. So we're going to use either a table or we're going to use StatCrunch. So the problem is find the critical value such the area under the chi-squared distribution to the right of the critical value is 0.05, assuming 15 degrees of freedom. If you use the table, which is in the textbook, step 1, draw the chi-squared distribution with the critical value and area labeled, which we've got. So there's our chi-squared. 2, use the table to find the critical value. So the critical value on the table gives you area to the right along the top, degrees of freedom along the column. So take a look at 0.05 tail, 15 degrees of freedom, and you get a 24.996. All right, you can also use StatCrunch. So I'll bring the StatCrunch over and we'll use the StatCrunch calculator. So in Stat calculators, there's chi-squared calculator. So if we want area to the right, let's see, our degrees of freedom is 15. And we want x greater than or equal to, and then put in the area, 0.05, because we're looking for the actual value. Then this will match your picture, and we get 24.99579. Okay, so you can use either the table that comes with your textbook or use StatCrunch. All right, objective number 2, we want to actually perform a goodness of fit test. So what a goodness of fit test is an inferential procedure used to determine whether a frequency distribution follows a certain specific distribution. So I'm going to go, let's read the problem that we're going to do first, and then we'll come back and look at each of these. So the problem, go down here a little bit, it says, one growing concern regarding the U.S. economy is the inequality in the distribution of income. An economist wants to know if the distribution of income is changing. So she randomly selects 1,500 households and obtains the household income shown in the table at the right. Table 2 also contains expected counts, assuming under the assumption the distribution is not changed since the year 2000. So we're going to see how to do that in just a second. Does the evidence suggest the distribution of income has changed since the year 2000 at the alpha equals 0.05 level of significance? All right, so how do we get these observed and expected counts? So let's go back up to the example. Finding expected counts. So the original table that we're given tells us the distribution of household income in the year 2000, but it has a percentage, and this is from the U.S. Census Bureau. So under 15,000, 7% had that of households have an income under 15,000. From 15,000 to 24,999, 8.6%. So these are given percentages based on U.S. Census Bureau. So to find expected counts, what we would do is we would multiply each of these percentages times the 1,500 that are in the sample size. The random sample was 1,500. So from that sample, we would expect for under 15,000 to take 1,500, the sample size, times the percent, 0.07, we would expect 105 out of her sample to be under 15,000. Then we multiply each by the percentage, 1,500 by each percentage, and these are called the expected counts. So if the income is the same as it was in 2000, these are the actual number of households we would expect to have the income levels. So now we have something called expected counts, and we want to take a look at what a goodness of fit test does. So to test hypotheses regarding a distribution, step 1, determine the null and alternative hypothesis. The null is that the random variable follows a certain distribution. For this problem, it's going to follow the 2000 Census Bureau distribution of income. Alternative, random variable does not follow the distribution. Notice there's no greater than, less than. It's just it does or it doesn't. Step 2, decide on your significance level. It might be given. Step 3, calculate the expected counts, which we have already done for this problem, and then verify the requirements are satisfied. So the requirements for this test, all expected counts are greater than or equal to 1, and no more than 20% of the expected counts are less than 5. So let's take a look so far for our test, okay? So we've got here the null hypothesis for our problem. The distribution of household income is the same today as it was in 2000. There's not a significant difference between observed and expected. So we've got the expected counts in our column, and these are from our calculations up in example 2. The observed counts are the actual data. So where did those come from? Those came from her study in 2013. And we want to know, do these follow the same distribution? Expected counts means that it would follow the year 2000. Observed counts are what we actually observed in 2013. Okay? So then the alternative hypothesis is the distribution of household income in US is different today than it was in 2000. The significance level was 0.05. Step 3, the requirements are met because all expected counts are greater than or equal to 1, and no more than 20% are less than 5. As a matter of fact, none are less than 5. So how do we conduct the test? So the by hand method, okay? So if you're going to do this by hand, we would compute the test statistic. That is, compute the chi-squared statistic. We would take the sum of all of the observed values minus expected, square them, and divide by expected. What we're going to do is I'll show you the p-value by hand approach, and then I'll show you how to use technology. Okay? So the by hand approach is we take each of the observed minus expected, square it, divided by expected, and we get a value for each row. Add all of those together, the sum of, and we get a chi-squared statistic of 10.105. Then you would find your p-value, the probability of getting a chi-squared 10.105 or greater. If you use the calculator, you would use second, go to the distributions. There is a chi-squared distribution, CDF, in here. The lower would be 10.105. Because we want to know the area to the right of 10.105. Upper would be infinity. And the degrees of freedom for this one is the number of rows that you have minus 1. So we have 1, 2, 3, 4, 5, 6, 7 rows. So the degrees of freedom would be 6. And we get an area of 0.1203. Okay. All right, so that's if we calculate by hand, okay? Use technology. The TI-84 has a goodness of fit test. So the goodness of fit test is in statistics, tests. Scroll down until you find goodness of fit. Chi-squared GOF test. observed, you have to put in your lists. Let's see, let me get out of here. In stat, in edit, enter your observed in list 1 and enter your expected in list 2. So you have to put the observed and expected values in up front. Then go to your goodness of fit test on the calculator. Chi-squared goodness of fit. Your observed are in list 1, expected in list 2. Degrees of freedom are the number of rows minus 1, and then calculate. So this tells us the chi-squared is about 10.105, and the p-value is 0.12. So these are the same results, much easier than doing it by hand, okay? Or you can use StatCrunch. So in StatCrunch, close that. I've got the income, I've got observed, and I've got expected. So you have to type in, you don't actually need the, the title or the labels, but you do need the observed and expected. So under stat, we would be doing goodness of fit, chi-squared test. Your observed are in the column called observed. Expected are in the column called expected. And then compute. So notice the chi-squared 10.105, p-value 0.1203. So it doesn't matter if you do it by hand with the calculator or with StatCrunch, you'll get the same values for chi-squared and p-value, and those are the two items that we need. So now what do we conclude? Okay, so step 4, it's the same type of conclusion. If the p-value, in this case, was greater than the significance level, so we fail to reject. If the p-value was less than the significance level, we would reject. So failing to reject says we conclude there's not evidence to show the distribution of household income in the U.S. is different today than it was in 2000. And different, it wouldn't be today, it would be in 2013. So that's a goodness of fit test on your calculator. So the types of problems that you'll have in homework walk you through how to find goodness of fit. So I did want to go over one called Binford's Law on how to find expected values. So the first significant digit in any number must be 1, 2, 3, 4, 5, 6, 7, 8, or 9. It was discovered that first digits do not occur with equal frequency. Probabilities of occurrence to the first digit in a number are shown in the accompanying table. The probability distribution is now known as Binford's Law. For example, the following distribution represents the first digits in 200 allegedly fraudulent checks written to a bogus company by an employee attempting to embezzle funds. Complete parts A through C. So this Binford's Law distribution is a set distribution that says if you have a random selection of numbers, then there's a 0.301 probability that your first digit is a 1. There's a 0.176 probability that your first digit is a 2. And each of these has a decimal that goes with it. So the fraudulent checks, these are the observed values. What we want to find is the expected values. So we have 200 checks. So to find the number 1, how many of those checks should have a leading digit of 1? Take 0.301 times 200. How many of those checks should have a leading digit of 2? Take 0.176 times 200. A 3, take the probability 0.125 times 200, and then you would keep doing that for each 0.097 times 200. You would keep doing that for each digit, 5, 6, 7, 8, 9, and those would be your expected values. Then you would use your observed values and your expected values and type them in the appropriate list, either in StatCrunch or in the calculator, and run your goodness of fit test.